Alright, hell yeah. So we have a problem from the Pathfinder. Now, I'm just going to go over the quick answer, because on a problem like this, that's going to be useful, because then you can kind of see it twice. We have gravity acting on a rod and a bead, and it's way out in space. The bead, though, is closer to the Earth, so it's going to have a gravitational, it's going to move, the acceleration is going to be faster. Now the force is going to be proportional to the different masses of those, and so that's kind of the cool thing. Mass drops out of the force of gravity. Because of F equals ma, that force is equal to ma, and so masses cancel on both sides. So we have kind of the generic form for the acceleration is gravitational constant, mass of the Earth, and then the distance away from the Earth. The cool thing I learned from this video is that, well, if you're on the surface of the Earth, gravity is going to be 10, radius of the Earth is going to be squared, and g equals m. And then this is an equation you can rearrange. I never knew this, that you could actually just solve for this gm term in terms of just, it's going to be 10 times the radius of the Earth. And so in this problem statement, that's what they give you. So we have 10 to the 1, 6.4 times 10 to the 6th, 6 million meters is the radius of the Earth. We're going to square that. And yeah, we're going to have 10 times 40 times 10 to the 12. That's going to be 4 times 10 to the 13 times 10 to the 1 is 4 times 10 to the 14. So that's pretty sweet. This problem is also kind of cool because we get to work with, powers of 10. Alright, so these beads are going to have two different accelerations because they're two different distances. Even though this distance is hella, we still have hella plus x, and then this is going to be hella of the rod plus the distance to the middle. For this problem, I'm going to say the distance to the middle of the rod is w. And just because I don't want to write L divided by 2 the entire time. So that's the notation that I use. And so the relative acceleration, and then this gravity, because this distance is like smaller, and the smaller number downstairs, this acceleration is going to be bigger. So we're going to take the acceleration of the bead. Gm divided by the distance to the bead, r plus x squared, minus Gm divided by the distance to the center of the rod, r plus w. We're just going to say half the distance is w, and not to be confusing. There you go. Cool. So you get this and you're just like, well, how do we actually solve for this without just throwing it into our calculator? And it might explode a little calculator just because the numbers are real big and stuff. Anyway, so what we do, so that's the only, well, there's two tricky parts of this problem. Is like, well, how do you subtract these? And then when we do, what do we cancel? You know what I mean? So we're going to go over that, try to do it very briefly. So to subtract these, we have to get the denominators the same. So over here, I need an r plus w squared. And so if I put that downstairs, I got to put it upstairs. This whole thing is just multiplying by 1. Same thing over here. We need an r plus x squared. Need to put it upstairs, multiply by 1. All right, now here's where, it gets a little bit tricky. But I go over it in the problem where you're going to have a power of x to the 4th down here. You know what I mean? And you're just going to have one of them. After you FOIL all this stuff, you're going to have a lot of other terms, but one is going to be the biggest, and that's going to be, I'm sorry, r to the 4th. This distance is going to be to the 4th. You might add it to an r to the 3rd term, but that's going to be so substantially smaller, and I go over that in the normal video. So that is kind of how you can get a fast answer. You can just see that. You know what I mean? That might be hard to see from here, but after you do problems like this, you'll be like, yep, and then watch the video. We make some ways to kind of show like when you can use this, like when you can just lop off all those terms. Okay, upstairs though, something's a little bit, more unique because we're going to have, this is going to FOIL to r squared. How I do it is just r squared, w squared. And then you're going to have that kind of middle term. R is going to multiply by w, and you're going to have 2 of those. So hell yeah. Same thing here. R squared plus x squared. And then r times x, and you're going to have 2 of them. Now we're subtracting those, so I just made them subtractions. So we're going to have this r squared subtract r squared. Whoa, those just go away. So now we actually have some normal terms. But look at this. This has an r in it. This has an r in it. These don't. And the thing that has an r in it is a 10 to the 8. The other things are just like 5 and 0.02, you know what I mean? So these just go away as well. And so now we can, so now we'll have 2r, so that's what, and we'll factor out that, and then we'll have w minus x. So we have 2rw minus x. We still have this multiplied by gm, divide by r to the fourth. We can cancel out an r, and so we get 2gm w minus x divided by r to the 3. Sweet, that's going to be our acceleration. Now what? Acceleration means motion, but it doesn't really spell out like the time involved to get this bead off of there. But we set velocity. Velocities are equal to 0, time's equal to 0. I'm just going to set this position equal to 0, and so then when we integrate, you get a number for acceleration. That's the other thing, is like, hey, we have to at least consider acceleration to be constant, and you know what I mean, and just hope for the best. We can double check that in the end. We do that in the video, and acceleration is pretty darn constant. Cool. So then we can just integrate and say velocity is at, position is 1/2 at squared, and it's this equation that we want to solve for time. Position of this bead, we needed to get it to x. So x is where we needed to get it. That's going to be 0.02, and we're going to solve for time. The 2 pops upstairs, divide by a, take the square root, and sweet. And so we have 2x. This 2 cancels the acceleration term, which has a 2 in it. And because the divide by acceleration, this part's downstairs, gmw minus x. The x is upstairs, multiplied by r to the 3. And so we have 0.02. That's going to be the distance the bead has to go. It's 0.02 meters. I shouldn't have written it like this. I should have done 2 times 10 to the negative 2, or even 2 up top and then 10 to the 2 downstairs. You know what I mean? Because we have 10 to the 24, 10 to the 14. That's going to be 10 to the 10, but now we have another 10 to the 2 downstairs. So that becomes 10 to the 8. That's the cool thing about working with powers of 10. You can kind of just see that and do it on the fly. So if this was 2, hey, this 4 makes this 16. You know, factor out that 4. 16 times 2 is 32. Divide by this 4.98. So we still got to take the square root of it. This is like the square root of 6 times 10 to the 4. So that's going to be 2.5 times 10 to the 4. And hell yeah, that's the quick answer. Stay tuned for the rest of the video to kind of go through it more slowly. And we do find a lot of tricks in here. And this is a pretty cool problem. Alright, hell yeah. Alright, hell yeah. So this is a problem out of the Pathfinder. Now, this is a gravitational problem. This is the Earth right here. And what we have is a rod that's 10 meters long, and it has a bead. The first thing that I ran into, because I did this problem where I thought this bead was 2 meters. So this is 10 meters, and I thought this bead was 2 meters from this end. I would never write a problem like this where you mix units. If I said this was 10 meters, I would say this distance is 0.02 meters away, but they just chose to use 2 centimeters. Now I get that, but man, my brain can't handle this. You know, if I'm saying the rod is 10 and I get to here, I'm just going to assume it's 2, I guess, you know, because the number comes first and then the description. I'm just kind of bad at reading maybe. So anyway, and then even just this, you know, I mean, why not just do 6.4 times 10 to the 6 meters? And or just even write it out, 6,400,000 meters. But anyway, so those things kind of trip me up. All right, so basically here's the whole problem statement. What happens is that you can treat kind of objects. Well, objects do have a center of mass, and it's the center of mass that's going to experience that gravitational force. And this works for round objects, but anytime you have a long object, this is an approximation. So just know that if the gravitational pull from this point is proportionately, or I mean it's the distance squared. So the force on this chunk of mass, the gravitational force towards the Earth, is going to be well, it's obviously less because it's farther away, but because it's a ratio of the distance squared, it's not linear. But when your distance is just hella, you know what I mean? We're talking 100 million miles away, 400 million miles away. That's how you would read this, you know what I mean? Just think 10 to the 6 is a million, and then you got 400. That would be 10 to the 8. So 400, hopefully I'm saying that right. Yeah, 400 million meters away. Okay, so, but yeah, so basically just the center of mass, so the distance from the center of the Earth to the center of this rod, that's what's going to drive the force of gravity. And then we have the distance from the center of the Earth to the bead. So we have a bead just kind of floating on this rod, but we're going to place the bead right there 2 centimeters away from the end of the rod. So that's all the distance that it has to travel. The reason when you let, and then the problem says you're just going to let this, you're going to hold it stationary. I mean, just pretend like nothing's rotating at all. You just have a chunk of mass over here called the Earth. You're this distance away, and slowly these two are going to be colliding with each other. These are nonsensical problems. Well, I don't know, actually. You know what I mean? Because like even when something is orbiting, it has a velocity, and typically, like that velocity doesn't change because there's no friction, and it just holds it into that orbit. It doesn't fall towards the Earth at all. Actually, it does typically the opposite, because the Earth might be losing mass, and so things still maintain their velocity. So that's the take-home point there, which is really fascinating. That's why, you know, we're not getting closer to the sun, even though the sun's massive. The sun is losing so much mass due to radiation and all that we are actually going away from the sun. Now, that's super slow, whereas the sun gets larger, it will engulf us. But anyway, it's just kind of fascinating. We think that two things that are gravitationally attracted are going to, hit each other. But all that gravity goes into the fact that things are rotating. You know what I mean? Just the fact that if this is the sun and this is us, we want to go in a straight line. We don't want to be orbiting around the sun, but the force due to our planet, and then the gravitational force between the sun and our planet is what's holding us along that circle. But it's just barely doing that, or an equal. Like that's from a physics perspective, that was the most amazing thing, where you're just like, oh, you have an aha moment. You're just like, whoa, like all that gravitational force goes into just holding that orbit, and there's nothing left over. Like we are literally not moving towards the sun on a yearly basis, and because the sun is losing mass and there's no friction out in outer space, we're maintaining that velocity, and so we're actually getting farther away. But as we get farther away, you know what I mean, there's a balance point. So because why? Because we would have less gravity. Or how does that work? Y'all, I'll have to explore that just a little bit. But yeah, there is it's a balance point. Just because like if the sun loses mass and you still have this velocity, yes, your orbit increases, but then it balances out. And so I'm actually not quite sure exactly why. Like why don't you just escape? I think it's due to the Alright, that's going to be for another problem, but I really want to derive the escape velocity problem. But anyway, let's do this one. So we have and what do we know? I think you need to use this equation, or just to know it. Force of gravity is gravitational constant. The mass, like one of the masses, that's the little m, probably out here. The other mass, in this case, it's going to be big M, mass of the Earth, and then it's going to be divided by the distance from the center of the Earth to the center of those masses. And so the generic form, and sometimes if you're just on the surface of the Earth, you would just say this is the radius of the Earth squared. But the generic term is gm, big M, and then x squared. You know what I mean? Hey, this is just a generic distance from the center of one object to the center of the other objects. Okay, so from the distance from the center of this object to the bead, so I'm just going to write bead. That's going to be r naught plus x naught. Now, for this problem, well, and let's do the rod, but I'm going to switch it up just a little bit. So to the center of the rod is going to be r naught. That gets us to here. And then we got to go halfway. So plus L divided by 2. But for this problem, I didn't want to write L divided by 2 all the time. Look at that. That's 3 strokes of the pen. So what I'm just going to say W is equal to L divided by 2. So this rod, there's W. Cool. And we have 2 of those. And that's just going to be way easier. So we're going to do R naught plus W. Okay, and then what we're wanting to know is all right, so I guess the other thing we need to write is F equals MA. So this is, we have something out. It's just floating out, especially things that are in outer space. Like there's not much forces on them except gravity. So yeah, we have a force of gravity. That's going to be this side of the equation, and that side of the equation is going to equal, well, if we're analyzing this bead, we're going to, circle it or draw a free body diagram, analyzing this rod. It has a mass. And so we're figuring out what the force of gravity on each of these is. And we kind of want them independent. So we're going to be, hey, the force of gravity of the bead is equal to mass of the bead times the acceleration of the bead. And it's actually, we want to know the acceleration of the bead. And so, but let's write out this whole equation. So we have the force of gravity. That's this equation that we put in. So we have gravitational constant, mass of the bead, mass of the Earth, and then the distance is going to be r naught plus x naught. And that's going to be squared. This is going to equal the mass of the bead times the acceleration. And you can see that the mass of the bead drops out. So we have this term for acceleration that is just this. And this is the acceleration of the bead. We can do that same process for the acceleration of the rod. And I'll just say acceleration of the rod over here, mass of the rod. But the distance is going to be r naught plus w squared. And then the masses of the rod would drop out. So I'm just going to save pen strokes and say the acceleration of the rod. And I'm just going to say the rod is w now, because this is the length that I'm attributing to the center of the rod, w. Okay. So that acceleration is going to be gravitational constant, mass of the Earth, divided by this r naught plus w squared. Okay, sweet. So this is going to be the acceleration of the rod. This is going to be the acceleration of the bead right there. And all right, yeah. So let's look at these again. Acceleration of the bead is gm. I'm just going to do big M for mass of the Earth. Cool. Divided by, and then I'm just going to do r. I'm just going to switch this to r, and this is going to be x. So r plus x squared, and then the acceleration of the rod is gm r plus w squared. So I thought this was a fairly decent way to simplify the problem, get rid of some of these letters, because when I'm solving this one was a little bit tricky. I actually had to look up how someone else solved it, but cool, I'm going to actually solve it a slightly different way. Same process though, this is one of those that's a trick one, where there's only one way to solve it maybe. Okay, but what we're going to see is that, why would this, that's the first thing, why would this bead slide off? Because it's closer to the Earth, it's going to be going faster, sooner, if that makes sense. And we can see that the accelerations of these right off the bat are going to be different. The acceleration of this one, the top is the same, but the bottom, look at this. So this distance is going to be shorter than this distance. So let's look at this one. The rod has a larger distance down here, and so we have a larger number dividing by a larger number. That acceleration is going to give us a smaller acceleration. Where here, we're dividing by a smaller number, and that acceleration is going to be a larger number. So here is going to be the larger acceleration. This is going to be less. So, you know what I mean? And acceleration is change in velocity. Right off the bat, both their velocities are 0. But we're going to change those velocities. This one's going to change more, and it's going to be fast. Even after 1 second, this thing is going to be going faster. And then this thing's going to be, well, kind of going slower. They're both going to be going in the same speed. So this is where we need the difference between, you know what I mean, maybe the difference between the velocities, or the difference between the accelerations. So that's what we have right here. We have an equation for the acceleration. Okay, so let's kind of start in on solving this problem. I'm going to rewrite this. Gm to the bead is just r plus x. See, this is why I got rid of some of the subscripts, because we have the rod. W is kind of weird for rod, but I'm fine with it. You might be able to get used to it. So we have the gravitation, I mean the equation is the gravitational constant mass of the Earth, the distance squared. That's going to be r plus half the distance of the rod. That's that w. So r plus w squared. Okay, so now we're cooking. This is going to be the larger acceleration. This is going to be the smaller acceleration. And so what we want is the difference between these. So our equation is going to be, hey, the acceleration of and we can get kind of technical. We can say the acceleration of the bead relative to the rod is going to be the acceleration of the bead minus the acceleration of the rod. So now we kind of have like this, you know, I mean, kind of frame of reference where all we're interested in is just the speed of this bead relative to the rod. You know, let's say the rod is stationary and then the bead is slowly changing its velocity. The bead has 0 velocity and then starts to pick up speed in that direction. And then at some point it's going to pop off the end of the rod. Alright, so that's kind of the general gist of the problem. Now, but now we have to just figure out like how to get an answer to this. So we're going to, let's write this out. We're going to say that this difference is going to be Gm. And then where are we going with this? You know, because that's the other thing with this problem. Like I threw it into Excel because I didn't know, you know, I figured we were going to get a value for that kind of relative acceleration. I got that. But by the time this bead pops off the rod, I don't know, maybe it's really close to the Earth. Who knows? But a problem like this is sometimes you just have to say who cares. And just, you know, for whatever, you know, whatever the relative acceleration is, sometimes you just have to be like, well, I'm just going to guess it's constant, you know, find the value for time, and then maybe go back and double check, you know what I mean? So, and yeah, we can do that at the end. And then I guess the take-home point is this thing's so far away that by the time it actually pops off, it doesn't even go you know, the distance doesn't halve. And with gravitational problems, if this distance halved, the acceleration would be 4 times greater. And so the relative acceleration would be 4 times greater. But this distance is hardly 1%. By the time this thing pops off, the distance doesn't... but that is kind of interesting. Like, the fact that this doesn't happen instantaneously, just because there's a difference in gravitational forces, it takes a long time, and we're gonna figure out if that's minutes or weeks or months. You know what I mean? So hell yeah. All right, so we have this. We have the acceleration of the bead that's going to be bigger. R plus the distance is r plus the distance to the bead. Squared minus Gm, and then we have r plus omega squared. And I guess this is the other thing, is this kind of blew my mind. So we can actually kind of slow down, because the general form for the force of gravity is gravitational constant, mass of the Earth, radius of the Earth squared. And so this was fascinating. And from this we have F equals ma. You know what I mean? So if we set this equal to mass times acceleration, because here's my force, that's what my force is equal to. We have this equation F equals ma. So this side is ma. And we can see that we can drop out of mass. So we can get this equation. Gm, radius of the Earth squared, is equal to acceleration. And what we know is that these three, and maybe you don't know, but these three equal g. And let's spell that out, because this is 6.6. Alright, hell yeah. So this will start the process of working with exponential, scientific numbers, 10 to the whatevers. Just think devil, I don't know, 666, that gives you gravitational constant times 10 to the, well, it's the negative 11. And this is 6.67 to be more accurate, but that kind of gets you going. Mass of the Earth is 6 times 10 to the 24. So I guess there's one more 6. So 6 times 6. But bottom here, you can, radius of the Earth, you can do this as 6 times 10. And you could even do, it's 6.7. Is it? Yeah, it's 6.72. But who cares? You could do it 6. I never even thought of that. You could do another 6.6. 6.66 actually gets you closer to, that's better than just 6.6. But 6.6 times 10 to the 6. Yeah. And then you're squaring that. But what happens is that you have basically 6. And then you don't have to keep these. These are just, what I like to teach is like, hey, this x can get confusing. It's a multiplication, but you don't have to hold those with it. So I can be like, hey, that's 6. Put this 10 to the negative 11 in parentheses. And this maybe gives you kind of permission to move things around as much as you want. This is going to be, when we square this, the same thing. We have 6 times here, and then we have, I'm sorry, I didn't do 10. And then we have 10 to the 6. And then when we square this, we're going to square the individual terms. So we're going to have 6 times 6, and then we're going to have 10 to the 6, and then 10 to the 6. Sweet. So this becomes 10 to the 12. This 10 to the 11 adds to 10 to the 12. We can just bring that downstairs. And this will be 10 to the 23. So sweet. And these 6's cancel those 6's. So it's really simple. You just have 10 to the 24 divided by 10 to the 23. I don't know if it's simple. It's just nice the fact that all that cancels so easily. And you just get a value of 10. And you're just like, oh, that was sweet. And so that's gravity. That's just 10. And so that wasn't actually what I wanted to go over. The trick that I never knew until doing this problem and seeing someone do it is that they got a value for GM. So so if these three things are equal to 10, and in the problem statement they give us this value of 10, and then they also give us this value of the radius of the Earth, which is 6.4 times 10 to the 6. Meters. There's a huge fluctuation between the distance. Oh no! Yeah, the distance. It's not 6 point. It's not 6.7. Sorry, it's like 6 point. It's 6,000,000 like 700 and 720,000. No, it's I forget 6 point. Now I'm confused because. 6,400,000 meters. I actually don't know, there's so many different radiuses of the Earth, of where you're going to measure. Like the radius from the center to the poles, radius from center to the equator. So it's just good to know that there's 6 million meters. At least get to 6 million. That'll get you going, and then figure. Now I'm at a total loss. I don't know what is accurate. But here for the problem, they say it's 6.4 times 10 to the 6. All right, so what I do want to go over is that we have this equation. GM radius of the Earth squared is equal to G. So this kind of blew my mind because I was just like, oh, I never realized I could move this equation around. And this comes up a lot. Anytime you have an equation with terms, you can rearrange it however you want to solve for whatever you want. You know what I mean? And so for our problem, we have this term, that's the GM. And so let's do that. Let's solve for GM. We see GM is G, gravity, that's going to be 10, times the radius of the Earth squared. Sweet. And let's do that one right now, because we have 10, and then we're going to have 6.4 times 10 to the 6, and we're going to square that. So this term for GM is going to be 6.4 squared times 10 to the 12. 10 to the 12, and then 10 is going to be 6 point, and then we have another 10, so 10 to the 1. And again, don't let these this x, get you down. We can just put everything kind of in product parentheses. So this is going to be 10 to the 13, and 6.4 squared. Well, we could do that. I'm just going to do 64 times 64, and this is going to be 16, 25, 24, 36, 38. Okay, so we have 40.96, which I'm just going to round, and I've already done this one, but it's just kind of interesting that now we're going to have 40. Let's just say 40, maybe 41. 40.96 times 10 to the 13. So we can move this decimal place 1, and now we got 4.096 times 10 to the 14. Or I'm just going to simplify this and just say, hey, it's 4 times 10 to the 14. So sweet. So now we have a value for GM. GM is 4 times 10 to the 14. And you know what I mean? Because this problem is a lot about just making sure you're okay with working with, what are these called? Scientific, are these exponential numbers? I have no idea what they're called. But just kind of the scientific notation. Okay, sweet. Because, yeah, we have 10 to the 14 up top, and then this radius is 4 times 10 to the 8. And guess what? We're going to square that. Alright, so I'm going to rewrite this, and we're going to figure out how to get a value on this. So we have that relative acceleration is GM radius to the bead squared minus GM radius to the center of the rod squared. Alright, so, and we want to get a value. I'm just going to say this is the acceleration we're interested in. It's the relative acceleration, you know what I mean, whatever. But yeah, it's just that this is going to be a value for acceleration. And yeah, you could just throw this into your calculator, and it's just going to pop out a number. So if you do that, you're just money, and then just go with it. But if you kind of want to, I don't know, like, why wouldn't you just use your calculator? This is kind of interesting because calculators are only good up to about like 10 digits. And, or numbers, or yeah, I don't know if I have that right. No, never mind. I thought my calculator only went to like 10 to the 10. But it might. 10 to the 10 or 10 to the negative 10. Does my calculator go 10 to the 99? I have no idea. 10 to the negative 99? I don't know. I'm in the process of getting a new calculator, so we'll see. But yeah. But this one, yeah, we can do it without a calculator. But now we have to subtract these two numbers. But how would we... Alright, so I guess let's just spell out how you can do the solution. When you get to here, you can make the denominators the same, and then you can subtract then you can do subtraction. Sweet. So to do that, I'm just going to multiply, well, I guess I'll write this out again. So we have gm r plus x squared, and we got to multiply by this side, r plus w squared. Sweet. And now we have to put in r plus w squared upstairs, because this equals 1. You know what I mean? And so we didn't change anything. Now on this other side, we'll have gm. We're going to have r plus w squared, and we're going to multiply by this, r plus x squared. And then we got to go r plus x squared up top. So we just need to make the denominators the same, and we're doing that by just multiplying, you know what I mean? So we just multiplied this on that side. And now, you know, these are flipped around, but the denominators are the same. It's just the product of those two. Hell yeah. And then we see that we didn't change our equation because we just multiplied by 1. These two things are the same. Alright, sweet. So now, I don't know. Like, I went through the entire process. Like, you don't have to do this. One of the comments on one of the videos like this is just like, if you were in a test situation, like, what would you do? You know what I mean? Well, you would realize, I mean, once you do this process, and we're going to go through the whole process, you realize that, oh yeah, there's a huge difference between r to the 4th and r to the 3rd. You know what I mean? So if we do r to the 4th plus r to the 3rd, so now we can talk about this, because that's kind of where we're going. So we have this distance that's 4 times 10 to the 8. And that's going to equal r. So let's see what r squared is. That's going to be 16 times 10 to the 16. And now let's do r cubed. That's going to be 64 times 10 to the 24. And holy hell, r to the 4th? You know what I mean? So we would have r to the 4th is, I don't know what 64 times 4 is. That's irrelevant. But this is going to be 10 to the 32. So here's how this works. If you just have like something that's 10, let's say you have something that's 10 to the 2, 10 to the 3 plus 10 to the 2. You know what I mean? So let's say you're going to add those up. This is going to be 1,000. Cool. And then this is going to be 100. So when you add them, you're going to get 1,100. You know what I mean? So that was, you know, like, yeah, that seemed important to add this, 10 to the 2. But now, look at the separation here. We have a separation of 8. So let's just do that. Let's say we have 10, let's say 10 to the, yeah, because this is, I mean, if this was 1, this is, I mean, this is 16, and then plus 8 is, you know, is that. So if I have 10 to the 1, cool. No, I'm sorry, 10 to the 9, plus 10 to the 1. You know what I mean? That's the same distance here. It's a plus 8. And so what's 10 to the 9? That's going to be 1 with 9 zeros. So that's going to be 1 billion, and now we're going to add 10. Okay, so, you know, if you got $1 billion and then someone gives you $10, well, I don't know. That's something. It's something. But, I mean, look, if you're just going to 3 significant digits, like, this is just meaningless. And kind of that's the take-home point. If you're adding 10 to the cube plus 10 squared, well, yeah, it does. Like, your significant digits do matter. But the second this thing gets more than plus 3, it really doesn't affect your significant digits. So maybe that's kind of the take-home point for this problem. Like, if you're interested in 3 significant digits, and you know, when you're adding terms that are, you know, much smaller, where the powers are more than 3, then it's probably, it could be safe to say, nah, yeah, like, it doesn't change this number. 1 billion is still 1 billion. Even if you added, so even, let's do this. So we have 10 to the 9 plus, and what did I say, a factor of 3? So we're going to add 10 to the, like 10 to the 6. And, but I said more than 3, so let's do 10 to the 5. Sweet, so we're going to have a billion. What's 5? 1, 2, 3, 4, 5. That's 100,000. So now we have 1 billion, no millions, but we have 100,000. Still, you know what I mean? There's 4 digits right there, and this is the 5th digit. Alright, so I think we kind of understand that process. But what I'm going to do is I'm going to go through this whole thing. So we're going to first do r plus x squared. Now, you can write it out and FOIL it. But I like to do this. I know mentally I'm doing this. And then I'm just going to, so what I do mentally is I just say, hey, I have r squared. And then I go to this term, and I'm going to square that term. So when I do the foiling, it's like I'm obviously going to square those, and then I'm going to like square these. But then I know that I'm going to have this times this, and then plus this times this. So I always do like this squared first, this squared second, and then I do kind of the funky term. You know what I mean? We're going to do r times x, but we're going to have to do that twice. So we're going to have 2rx. Alright, sweet. So that's the first term. And now we still got to multiply it by this. So let's do that same process. We have r squared plus w squared plus 2rw. Sweet. Okay, and now we have to multiply these out. And it's kind of a fun process to do, but even right here, yeah, even right here, if we threw in this value of r, this is 10 to the 8 squared. This is 10 to the 16. And then we're going to add it to 10 to the 8. And so again, this is meaningless. This is absolutely meaningless. This is point 2, x is 2, x is, I need to rewrite this. X is 0.02 meters. So, and we're squaring that. This w, and then w is going to be 5 meters. So those are the two values that we're using. This is x, and then this is w. So, you know what I mean. So that's kind of the take-home point of this problem, is 10 to the 16 plus 0.02, super meaningless. But even 10 to the 16 plus 10 to the 8, we just showed that that's meaningless. And so this whole process was just showing that like you could do it fairly fast. You could see that we're going to have just one, after this whole process, we're just going to have one r to the 4th term. So let's do this process. We're going to have r to the 4th. And then I'm actually going to FOIL this one. So we have r to the 4th plus r squared w squared plus r squared. No, this is going to be 2r cubed. This is going to be r cubed. So maybe that is something, but still no. Because we already did this. We have 10 to the 24 for r cubed. And then r to the 4th is 10 to the 32. You still have plus 8. Still meaningless to add that. Okay, hell yeah. So those are going to be the first 3 terms. Then we're going to have r squared, x squared. I always try to do the bigger term first. And then we have multiply these two plus x squared, w squared plus 2r x squared w. And then we'll FOIL these ones. 2r squared x plus 2rxw squared, and then plus 4r squared xw. And so that's our bottom term, and you can see that just all this is meaningless. So that was the take-home point. We just have one r 4th downstairs, so this can just be r to the 4th downstairs. But now let's go upstairs because something interesting might happen. Okay, hell yeah. We're gonna factor out the GM, and then let's square these. Oh well, I should have just squared these first. So we're gonna have r squared plus w squared plus 2rw, and then we're gonna subtract it by this. We're gonna have r squared plus x squared plus 2rx. And then I put parentheses because when we subtract this, we have to subtract each of these terms. So we have r squared subtract r squared. Cool. Those drop out. Now we have w squared subtract x squared plus 2rw subtract 2rx. Now here you might have to get just a little bit, you know, like you can see that like this is real small. You know what I mean? We already have this term with an r. That's 10 to the 8. And then this term doesn't have an r in it. You know what I mean? So it's r to the 0. You know what I mean? So again, if it's more than 3, that's kind of like what I've been learning from this problem. It might be meaningless to add, and it's 8 away. So these can just drop out. But let's FOIL this through. So we have, or factor the 2 out. So we have 2, and then we have we have 2r, and then we have w minus x. And in the video that I might put in the description of someone who does this, they even just say that this w minus x is just L divided by 2. They were saying that this 0.02 millimeters, because it's only 2 centimeters, is such a small distance that it's even similar just to 5 meters. You know what I mean? So they even dropped that term out and just changed this to L over 2. But I thought it was good to actually still add this, you know what I mean, because it adjusts your problem, you know what I mean, just by a little bit. And so we still have a multiplied by gm here, so that's the only thing. We have gm factored out, and then we just subtracted those 2 terms. Cool. So this whole thing, this acceleration, is going to be 2gm times this r term, w minus x, divided by r to the 4th. And you can see cancels one of those r's, so we have 2gm w minus x divided by r to the 3. And it's just kind of fascinating that like what we did was totally legitimate, and we get down to the driving terms. Like all these terms are important. Like we can't do without them, but all those other terms we could surely do without. So I'm going to rewrite this. So we have acceleration is 2gm w minus x r to the 3rd. Now we still got to do something with this. So what we have to do with it is from the kinematic equation. Like I said, I'm just going to assume that this is a constant. And so well, yeah, let's go back to this. If you drop something off a cliff into some water, gravity is 10, our velocity here is 0, our position is 0, and so how to do the integration? We have acceleration is 10. You know, this is dv dt. You can separate variables and integrate to get velocity. You get your dt over here, but yeah, you get velocity as 10t. Do the same thing because this is dx dt. Separate variables and integrate. You get position is 5t squared, which the general form is like, hey, 10 was the acceleration, now we're to 5. That's just 1/2 acceleration t squared. This is plus initial velocity, and then this is initial velocity t plus initial position. But we go to our problem and we see that this thing has 0 velocity. We're just going to choose the bead to be our initial position of 0. And then we just want it to go a distance of 0.02 meters. So that's kind of where we're at. And so we're basically going to have this general form. Acceleration is just a number for acceleration. Velocity is acceleration times time plus the initial velocity is 0, so we're good there. And then position is going to be 1/2 acceleration times time squared, plus the initial position is 0. So there's our equation. You know, knowing that this is the acceleration, now we can solve for time because we know this position, because we want the bead to be at x. You know, this distance, we want x to be 0.02, which I'm saying is x, the distance of the bead. I'm saying this value is x and this value is r. I just dropped the naught because it's just one less stroke of the pen. Alright, sweet. And then we can just rearrange this equation to solve for t. So t, we bring the 2 upstairs, divide by a, and take the square root. So let's do 2x divided by a, square root. So that's all I did. I just said, hey, let's solve for t, get that 2 over there, a downstairs, and take the square root of it, and then t's all by itself over here. And then obviously flip-flop it. Okay, so let's do that. So we have t is equal to the square root, and we're going to have 2 times x, and now we got to divide by a. So a is this, so we're going to divide by 2gm w minus x, and then we have this r to the third term up here. And this is going to be the time that the bead will pop off. And so we can still basically do this without a calculator. 0.02 is this distance, 0.02 meters. And I'm going to do 1, 2. I'm going to say that's 2 times 10 to the negative 2. So x is 2 times 10 to the negative 2. W is 5. W minus x is 4.98. I'll just use that. I mean, I guess I didn't need to do... yeah, no, I do like to get things into scientific notation. It's good practice. So let's do that. So we're going to go through here. And how do I like to do it? I like to do it like this. So we're going to have 2. This x term is going to be 2 times 10 to the negative 2. So I'm going to write 2 here. But I'm going to write the 10 to the 2 downstairs. That's 10 to the negative 2. Just bring the 10 to the 2 downstairs. Now this r cubed term, we said r was 4 times 10 to the 8. Squared is 16 times 10 to the 16. And then cubed is going to be 64 times 10 to the 24. So there we go. So we're going to have 64, and then we're going to have 10 to the 24. All right, sweet. And then we're going to have a 2 right here. This GM term is going to be 4. Oops, I don't like to do those x's. 4, and then we have 10 to the 14. And then this term is going to be 4.98. And I don't know, sometimes I do like to do parentheses, because then it just gets all your, I don't know. Yeah, I didn't mean to do that in parentheses, but there you go. So now we're going to cancel the 10s. 10 to the 24, 10 to the 14. This is going to be 10 to the 10 up top, but we have a subtract. So we're going to have 10 to the 8. See how I got that? So we have 10 to the 8 up top. This 2 is going to cancel that 2. Sweet. This 4, this could get that to 16. This goes to 32. So we're going to have 32. We have this 10 to the 8. We're going to divide by 4.98. So that's kind of the simplicity of if you get things in values of 10 and values of those constants, you know what I mean? Hell yeah. The only thing left was this 32 divided by 4.98. And now we just have to remember to take, I never remember to take the square root, but there you go. So this time value is going to be the square root of 32 divided by 4.98. And then we'll have times 10 to the 4. So there's our value of time, and let's see what this is. 32 divided by 5. That seems like 30 divided by 5. That seems like 6. It's going to be just a little bit higher, so we have the square root of 6. Sometimes this is very good. If I have the square root of 4, that's going to be 2. Square root of 9, that's going to be 3. Square root of 6 is going to be somewhere in between. It's like 2.5. So this answer, without a calculator, actually does come out to 2.5 times 10 to the 4. So that's going to be our time value that's going to take this bead to pop off. You know what I mean? If you do this in your calculator and then divide by 3,600, and let's do, I'd never even thought about that. You know what I mean? So we would divide by 3,600 to get hours. Well, why not just divide by 3.6 times 10, what would that be? 1, 2, 3. 3.6 times 10 to the 3. And then you can just easily see, like, oh, I've never even thought of that. This is why powers of 10 are so powerful, because you're just like, whoa, it was very easy to divide by that. And I can just see this is, you could just call this 1. 2 divided by 3, whatever. You know what I mean? But 10 to the 4 divided by 10 to this gives us a factor of 10. So we're going to have 10 hours. But it is 2.5 divided by 3.6, so we could modify. Maybe it's 7 hours, and that's actually the right answer. So there you go. So you have 7 hours, or 2.5 times 10 to the 4 seconds to do this. And just a cool problem, because it really helps your skills with powers of 10. And hell yeah. And so the only other thing that I wanted to check was if it takes this long, aren't these objects going to be closer to the Earth? So let's do that. So let's say we did get this value of 2.5 times 10 to the 4, and we have the generic equation that acceleration is gravitational constant gm divided by the distance. And the general distance is just r. So this is our acceleration. Yeah, this is the acceleration of these two objects towards the Earth. It's not we're not interested in the relative acceleration. We're actually just, hey, these things are speeding towards the Earth, and we can use that kind of generic acceleration is g, or acceleration is 10. Velocity is at, position is at squared, as long as velocity is 0 and position is 0. So we're going to do that same thing. So these things are both velocity 0, position 0. The acceleration is going to be this value. And so we want to know the position. Okay, sweet. So we want to know the position. And this is going to be 1/2. So we have 1/2 at squared. So let's do that. And we just because if we know that if the position is 1/2 r, then our acceleration term is going to be a multiple of 4. But let's see what we got. So we're going to have 1/2. The acceleration term is gm. That's going to be 4 10 to the 14. We already know that. And then divided by this r term is 4 10 to the 8. But it is squared. So sorry about that. We're going to have 16 10 to the 16. Cool. So that's the So we got the 1/2. We got the acceleration term. And then we have t squared. That's going to be this. Again, that's going to be like, what did we say? 6? Yeah, we thought it was 6 times 10 to the 8. So, yeah, so close enough. Okay, so we have, and this is our distance. So these almost cancel. We're going to have 10 to the 6. Cool. And now we're going to have, what else cancels? This 4, this turns to 4. This 2 makes this 8. And then this 6, this goes to 3/4. So we have 3/4 times 10 to the 6. I don't know, let's just call it, let's call it 10 to the 7. Yeah, so we do have an appreciable distance. You know what I mean? So if this was 4 times 10 to the 8, let's write that. 4 with 1, 2, 3, 4, 5, 6, 7, 8. And now we have, let's write this out. This was 0.75 times 10 to the 6, which was going to be 7.5 times 10 to the 5. That's all that's going to be. So we're going to have 1, 2, 3, 4, 5, 7. So this is 1, 2, 3, 4, 5. And then, because that's 6, that was going to be 0.75. So there you go. Now, alright, sorry about that. But now the question is this distance like significant? Because this distance was going to be less, so it's a minus. And I don't know. I mean, this is going to be 3, this is going to be 9, 9. And so we have 0, 0, 0, 0. Holy Toledo. So this has to go to 9. There we go. 5, 2, and then 9, 9, 3. So, you know what I mean? It went from 400 million to 399.25. So it's something, but it's definitely not half. I said if this thing half the distance, we would get 4 times. I mean, to get 2 times, if the acceleration doubles, we would have to be at 3/4 of the distance. We would have to be at 300,000 miles. And this is such a fractional change in distance that if you run through it, it's hardly anything at all. And so I did it in Excel, and it was, so this time is 7 hours. And let me print off that Excel just because that would be kind of a neat way to end this video. Alright, hell yeah. So the difference was 74 seconds, and I thought that was kind of interesting. So these accelerations are the same, but we have an the relative acceleration difference was like 6.225, and with that change, the relative acceleration distance was going to be 6.26. So it went from 6.22 to 6.26. So that is something, you know what I mean? Well, it's 6.26 times 10 to the negative. I guess, yeah, it's but no, that is this. It went from 6.22 to 6.26. So that is something, and it was here where the acceleration of these things, you know, just the acceleration of them towards Earth was 0.0025. And after 7 hours, that acceleration was going to be 0.0251. So you do have an increase in acceleration. So I thought that was a fascinating thing to go back and check. But, I mean, just in general, the bead's going to pop off in 7 hours. With the modification, it's going to pop off 74 seconds sooner than you thought. So there you go. So, but that's it. I don't know. It's just kind of a cool problem because it's still like the take-home point is all this stuff is completely irrelevant. You know what I mean? Once we're splitting hairs, yes, like the distance this has traveled, this was the only thing that was kind of significant. We have a distance of 4 times 10 to the 8, and after it pops off, we moved a distance of 7.5 times 10 to the 5. And again, maybe making some rules in your head. Look at this. We have 10 to the 8, and then we have 10 to the 5. When we add those, could we, should we? Yes, we only have a plus 3. And so it probably is going to be like a, you know, something. If it's plus 4, plus 5, plus 6, you get into the realm of ridiculous. You know what I mean? There's no reason to be like, hey, I have $1 million. Ooh, I found another dollar on the street. Now I have $1,001,000. To some, you know, you mentioned money. Hey, that's significant. It's $1. But for problems where you're having, you know, where r is 10 to the 8, r squared is 10 to the 16, you can't add those. You know what I mean? It's just meaningless to add. So that's kind of the take-home point on this video. And it was just, yeah, I learned a lot from, this was one of those where I gave it my best. I was able to do it in Excel. We'll see if I post that video at a later date. But I think this was better, just to do the clean video. And I might clean up that other one in Excel. Because what you can do with this is just like, hey, I can just right off the bat get an acceleration. And, well, no. That wasn't, well, no. I mean, yeah, I knew that I needed to find the relative acceleration. And then the question was like, well, when's it going to pop off? So I did use Excel. Anytime that you have acceleration, that's just change in velocity, change in time. So as long as your change in time is like 1 second, or you know, or some number, you can say, hey, I can find the change in velocity. That's acceleration times change in time. And then so even after a second, I have some sort of change in velocity. And then my velocity starts at 0, at t is equal to 0, and then at t is equal to 1, hey, we get some. And then you do the same thing. Once you have this velocity, hey, you're going to get an average velocity, and you're going to do that same thing. That average velocity is change in position, change in time, and you can say that average velocity times change in t is change in. So you can find your change in position. Position is 0. Hey, now we have a value on position. But that is such a good way to do a problem, is just throw it into Excel piecewise, because I don't know, just like I think the integration can be confusing, and you know, I think it can be fast just to be like, hell yeah, if I have an acceleration, if I can get a number on my value for acceleration, I can throw it into Excel and at least get close to an answer. The only issue was when I did this for the first time, I thought this 2 was 2 meters. I literally thought it wasn't drawn to scale, or it kind of halfway was. If this was 10, this was 5, and I was like, well, it looks like they drew this at 1 meter, so I just assumed that it was 2 meters, and right there, I had no idea it was 0.02 meters at 2 centimeters. But I still got an answer. It took 200,000 seconds, and because Excel, I was able to get that answer, you know, almost 100% correctly, just using a method that I know how to do, and I can make less errors. And that turned out to be 178,000 seconds. And let's leave it like this. How many hours was that, or how many days? Because this was if this was 2 meters away, and I got 200,000, and we're going to divide by, so that's going to be 2 times 10 to the 5, and we're going to divide by 3,600, which is 3.6 times 10 to the 3. So we have basically 3.6 times 10 to the 3. Dividing these, that's basically 1, and we're going to have 10 to the 2. So we're going to have 100 hours. So in that case, that's going to be 100 hours, 24 hours a day, 5 days. So if this bead is 2 meters away from the end, it's going to take 5 days. If it's 2 centimeters away, it's going to take 7 hours. So yeah, it's kind of cool. Alright, so thanks for joining me on this one, and guess what? That's a video.